Hey everybody. So this is going to be the third in the developing series for people who are writing code against Couchbase. And in the previous two sessions, we talked mostly about the document model and how you would interact directly with your data from your application tier for your interactive code path. You know, the stuff where having a sub-millisecond latency is really important. For this talk, it's going to be really an introduction to what you can use the query engine for, and a little bit about when to use it. But mostly we covered when to use it in the last talk. So I'll just kind of reiterate that quickly. You're going to want to use the key value interface. You know, get, set, multi-get, cas, update, those operations whenever you can when you're doing interactive updates, you know, on behalf of a user or you know, loading some data to show a user. And the reason why is that the latencies are just so low. So having a document with a bunch of other document IDs in it and then going and doing another, you know, secondary load based on those, and maybe those even have documents, you know, load something else based on those. That was all what the previous talk was about. But it's a pattern that's been with us for a long time as a key value store, and essentially the message of the previous talk was, don't throw that pattern out. That pattern is still valuable, even though we have this powerful query engine. And so if you're going to use those key value patterns for your interactive kind of high performance code paths, well then when do you want to use the views? And although there are some use cases where you'd put the views in an interactive you know, sort of the user's waiting on a view to show them the work they just did. For the most part, the views are going to be, you know, think of it as a reporting engine that can give you insights into the data that's already there. And so this might be something like, you know, you're already keeping track of comments on blog posts, but you decide after the fact that you want to be able to give comment authors the ability to browse through all the comments they put on the site. And you know, that doesn't have to be super fast, right? This isn't the really highly interactive portion of the site. It's, oh, I want to look at my archive and browse back into ancient history. Say you want to do that, that's a great use case for views. So just having set up kind of, you know, when is the right time to use views? Now, here's what we'll talk about. So before you can really use the view indexes, you know, to the best of their potential, you have to understand the life cycle. And so the differences between the different components of the storage and indexing and query system, and you know, when they're active, and when you you know, which parts of your query are dynamic and which parts are you know, essentially building an index to run dynamic queries against. So that's what we'll talk about first, is that life cycle. And then we'll talk a little bit philosophy about emergent schema and how to, you know, deal with messy data. And then we'll finish up by looking at some of these patterns that you can directly use in your application to get stuff done with a view. So the view lifecycle has these three main phases that I'll talk about. There's defining your index. So this is the part where you write some code to build an index. Then there's the part where Couchbase server takes that code that you wrote and runs it and actually builds the index. So it takes the definition and builds the index. And then there's the part where you ask Couchbase server to apply a query to that index and give you the result set. So those are the three distinct phases, and there's a little bit more nuance than that, which I'll talk about at the end. So how do you define a view? Well, you do it in JavaScript, and that may feel different from what you're used to with a relational database, but it's not all that different. I'm drawing this analogy here between creating an index on a field of a row and writing some JavaScript that picks a particular attribute out of your JSON to index on. So this is the definition. In JavaScript, what it's saying is, if the doc.type, which is again, like, that's user data, that's not some Couchbase thing, that's just doc.type is something the user put there. If that's equal to brewery, and the document has a city field in the first place, well, let's index it by the city. So that's what the call to omit is. So we've got, you know, some JavaScript saying only under these conditions, and then there's some JavaScript that says index this. And so the emit call takes two arguments, the key and the value. And I think most of my examples in this talk, the value I'm leaving blank. You can piggyback some data into the index using the value, but the key is really, that's where the action is. It's how the lookups are performed. So at the end of all that, you're going to end up with a sorted data structure that allows you to pull chunks out together. So, A, B, C, all in one query. And I'll talk about that more in a second, but this is kind of, this data structure on the bottom is what we're getting toward when we define the JavaScript function on the top. So I'm not showing this here, but just to give you the context of what you'll be doing, and you'll see some screenshots in a few minutes to show you this, but the easy way to define one of these map views is just to go into the administration console and click on view and go down and type it in and hit save, and then you can run your queries on that. There's also a distinction between a development mode and production mode, and we don't need to get super into the details, but development mode is meant to experiment when you're trying out things and writing it. It's going to be a lighter weight, faster process. It's not complete over the whole data set. And then there's production mode. When you hit deploy into production mode, it's an online operation, but it is going to be taxing on your hardware. So you don't want to just be deploying into production all the time. That's what the development mode is for. So we've defined the index. We've got this JavaScript function. You can hand it a document, and it'll hand you back a key from that document. It might even hand you back more than one key. That's what the definition phase was. So now we're going to do the build based on that function. So we're building that B tree structure that we kind of saw on the previous slide. And the way it works is the JavaScript runtime is launched and initialized. And then we teach it all the index functions that you've got. So if you have 12 different indexes, now you've got this JavaScript runtime that knows all your index functions, and it's ready to go. And then we feed it one document at a time. We say, hey, here's this document. What is it indexed to? And it says, oh, that document, it doesn't index to anything. And you hand it to the next document. It says, oh, this document indexes to San Francisco. And you hand it to the next document. It says, oh, that doesn't index to anything, right? And you hand it, and so it's a linear process. It's MapReduce, just like the other MapReduce implementations out there. The mapper phase has to see every document. What's different, and it's quite different from, say, the Hadoop model of MapReduce, is that our indexes are maintained incrementally. So that's why I used that analogy of the create index on a table, from a relational database, is that once you've defined an index in RDBMS, you're not going to think, like, is that index lagging? Do I need to kick that index to bring it back up to date? It just handles it for you. Couchbase is the same way. So you've written this function, and it's going to run on every document as it changes and mutate the index data structure to make it so it's always giving you a consistent snapshot of what the data bucket contains. So it's a fairly heavy weight, as I said, deploying a new view because it has to visit all the documents. It's not as heavyweight as it could be because those documents are spread evenly across the cluster. And if your application is going to be one that uses views really heavily, well, maybe you'll run 10 servers instead of 5 servers. And so then it cuts down on how heavyweight of an operation it really is. So this build is all done. The view definition is replicated out to the entire cluster. And then each server node builds its own little index inside that server node. And now we're ready to query it. So you've got to build the index first, and then you can query it. So here's what it looks like. We've got the index. We've got 3 of them here because we're running 3 servers. So I've kind of got 3 copies of the index at the bottom. They're all going to be subtly different, right? This server has 1/3 of the data, this server has 1/3 of the data, and this server has 1/3 of the data. So you're going to have different people with the last name starting in A on each server. And when you run a query, then it's distributed. First, it's scattered out to all the servers, and the result set is gathered up and sent back to the originating client. So that's the scattering and gathering work can be done by any cluster member. So your SDKs are just randomly picking some box whose job it is to babysit that view for you and send you the result set. Now, what does it look like to query this thing? That was a little bit of what's running under the hood, but the same data structure, very simple. The queries that you can do within it are they're sort of all a species of what's the clever thing I can do with this very simple underlying data structure. And all the data structure has to offer you is it's got stuff already sorted, right? So if you want to find everybody whose last name starts with the letter A, that's cheap. And I'll talk about this in the second half of the presentation, you can do aggregations on top of those ranges. So if you want to ask how many people have a last name starting with A, and the answer is 230 million, that's going to be almost instantaneous to come back with a response. It's not like MySQL where it's going to go and add up everybody, one at a time. So those aggregates over the contiguous key ranges in there are extremely high performance for the data volumes that they're dealing with. And so it's kind of a game changer for incremental lightweight analytics workloads. If your queries are simple, but you need the answer in real time, we can offer that, or in near real time. So a little bit more about the implementation and some of the performance hints, some of the options that you have. Just by the nature of the view system, it's on disk. It's on, if you've got 10 cluster members, it's on 10 disks. It's all spread out. It's not in RAM. It's not sub-millisecond latency. It's a few milliseconds of latency. And so we have some hints that you can give the system to tell it, whether you care more about speed or more about consistency. So by default, what we run in is this update after mode, which doesn't make any sense until you understand what updating is. So we've been through this. I described the life cycle of a view. There's define, build, and query. Well, in real life, you define it, you build it, you query it, and then you change some data, and then you bring it up to date. You do some more building, and then you query it again, and then you do some more building, and you query it again. You're not going to be changing the definition, but the underlying data is always changing as your users are interacting with your database. So now you've defined the view, you've queried it, you got a response back, the user did some work, and you query it again. What do you want to have happen? You have some choices. By default, what we're going to do is we're going to give you the old answer because we can give it to you right away. And maybe that's okay, especially for aggregations and kind of statistical work. It's a little bit of an old stat, but maybe it trails a couple of seconds behind your user activity rather than being immediate. So that's the default. After we answer your question, we're going to do that build phase. So the default is that we've got it all built. You fire off a query, we answer it, and we do some more building. So we're ready for the next query. But this is great if you're doing aggregations and kind of real-time statistical work. If you want to read your own writes, it's not that fun because you did a write and then you queried it and you saw everything but the write you just did. That's not so in those cases, that's when you'll want to use this performance hint that says, I care about consistency. I'm willing to wait. If it takes a half a second to display or a second to display to the user just saved it and they care about that it's there. They're just going to hit refresh if it's not there anyway, so we may as well have them wait. So that's the sort of the broad performance hints. There's the default, and there is no, I would rather wait and get the correct answer. And then there is something that's even more relaxed than the default, which is just because I ran this query, don't build anything. Just give me answers. All I want is answers. I'll tell you when I need you to build the index some more. And so that's what stale equals OK is. And so if you only use that, then your indexes are going to fall behind until our automatic background process brings them back up to date. So those are the three options. Again, if you find yourself wanting to use stale false for a lot of stuff, that might be a sign that you should look at some of the patterns I talked about in the previous discussion. some of the more document-based patterns. So while we have this slide up, so the question is, if you're doing a set from an SDK, and then you're reading the view, there's no guarantee that view is going to contain the write you just did. And that's true, and assuming that your window is narrow enough, pretty strong chance it's not going to be there. So if what you really need is absolute consistency of I'm writing this and I'm going to see it in the next view query I do, you've got to do two things about the asynchronicity. You've got to observe that write, and observe it till it gets to disk, because the views all operate at the disk layer. And then once that write is to disk, then you go and query the view using stale false. And so you're kind of hitting these disk latencies on both ends, and for certain use cases, it's not acceptable, right, as a performance. But for other use cases, it's exactly what you need, right? So yeah, so there's in the question, a little bit of a contrast between 1.8 and 2.0. In 1.8, first of all, we don't have the view engine at all. And so we don't have the observe functionality either. Look, I don't want to go too far into question mode, but if anyone's are related, oh, that's a great question. So the context of all of this stuff, the question is, where do these live when you define them? They live in a bucket. And they're actually grouped by a thing called a design document, which might be a little advanced for this talk, but essentially, like, you've got 100 views on your bucket. Well, maybe 10 of them are in this group, and 20 of them are in this group, and those are all maintained batch-wise. So the typical advice is, have them all together in one batch, because you probably don't have that many views, and you're better off maintaining one batch than 10 batches. So yeah, one more question, then we'll get back into it. Back there? Yeah, so the question is, what is the performance impact of the views? And so there's kind of two answers. One is that on the CPU side, kind of the actual work of deciding whether or not a given document is indexed by a given view, that's free. It's all the I/O associated with it on either end that's a pain. So if you have 100 views, but your average document only is indexed by 10 of them, the cost that really matters is when you're building those indexes and keeping those sorted sets on disk. What we do is we turn the document into JSON and we hand it off to JavaScript land once, and then it runs all 100 functions on it. So the actual execution time of the function is essentially free. All right, so yeah, I mentioned earlier the development versus production views. And this is a slide to kind of illustrate the difference. Most of the time when you're exploring new functionality, you're going to be in development mode. So that means every time you save the view and then trigger a build phase by querying the view, it's actually only working on like a random small subset of your data. The idea being that you can get an answer back right away from this representative subset, and it tells you whether or not, for instance, you had a syntax error in your view, or if it even sort of does the thing you were looking for in the first place. Maybe you're running a regex in there to drill something out of a field. You might want to test that regex on something other than 100 million documents before you click go. So that's what development views are for. And by default, when you're working in the admin console, you can only edit development views. So you do all your work there, and when you like your view, you deploy it to production. So a production view runs over the full data set and does all that scatter gather stuff and is built up on all the indexes and maintained and compacted by our engine. All the features apply to the production view set. So don't run the development views in production by accident. But aside from that, the only other nice little nuance here is that when you deploy to production, there are some checks in place to keep you from taking an index that's being actively read away from your users. So that's nice. You can get avoid having any downtime while you're swapping from one index definition to the new one. So let's talk a little bit of philosophy. And this is really just the same message I keep delivering over and over again about not stressing too much about your schema. I've been helping people with applications on top of NoSQL platforms for like 3 or 4 years now. And half the time when somebody gets themselves in a real bad trouble, it's because they were trying too hard. They were overthinking it. broke everything up into lots of little tiny documents and had some really crazy MapReduce that did some scientific awesome thing. But then I look at it and I'm like, hey, if you just took your really crazy MapReduce and made it into 4 simple MapReduces, and yeah, you would have 4 queries instead of 1 query at the end of the day, but the whole performance of the overall system would go up by double or something. So not overthinking it is important. And I guess the example that I like to give about not overthinking it is, and I mentioned this story or this example in the last talk, but the common project these days, like if you go to a hackathon, if you start a new startup, if it's day 1 on an application, a lot of people's application workload is, let's take this data stream, the Netflix API, the Twitter API, the GitHub API, and let's dump it in this bucket and let's make sense of it and let's layer our own value on top of it. And if that's your workload, you're probably not very well served by parsing the Netflix API and injecting it into a highly normalized relational database schema on your end. You could do that, but it sounds like a whole bunch of pain and wasted time compared to just, you want to stick that JSON somewhere and query it later. And I think most of us are comfortable with that now. Or maybe you just stick it in flat files and run regexes over it, but that's a lot easier than building a schema that can ingest that data, and then Netflix changes the data type from a string to an integer and your computer's crashing and you don't know why. So just store the JSON and make sense of it later. And that story, I hope it resonates with people. I'm talking about some third-party API you don't control. What's kind of the new thing for me, my realization is that, well, if that's how I feel about third-party data I don't control, I should feel about that about my application's user data as well. I've got a mobile client that's been installed via the App Store, and it's interacting via version 1 of my API, and that's saving these JSON structures to my database. And then I do an upgrade, and I ask all my users to upgrade to the latest version of the mobile application, but only half of them do, right? And the old ones are still running the old version, and the new ones are running the new version. And then you come out with another new version that does some new stuff, and now you have 3 versions running. And so if you start to think of your user data the same way you would think of data that you're pulling off the GitHub API, that's going to, I think, simplify things and have sort of, there's still thought to be done, but if you start with that as your baseline, you're going to end up in a comfortable place, I think. So the phrase I like to say here is that what you want to do is capture the user's intent. If you were building a relational model, the phrase would be different. We'd say, we want to model the world. We want a relational database that can't contain falsehoods, based on its schema. But instead, what we're doing is we're saying, the user told me this, I'm going to save it, right? I mean, maybe, you don't want the user to say, here's a photo from Frank, when really that's Chris. But, as long as your basic security checks pass, these days I find less and less value in nitpicking the format of a date time stamp or something. So let's look at some patterns. What can we do with this view index? The really simple thing is just look up something by an attribute, the really most basic secondary index. So let's find the beers by brewery ID. Each beer document contains in it a brewery ID, so we're going to build an index on that, and then we are going to have this result set. So I'll zoom in on these and we can talk about it. So here's the view function itself. It's got those 2 arguments, the document and then the metadata. And here we only care about the document. So if it's a beer and it's got a brewery ID, then we're going to index it by the brewery ID. And it's always helpful to do defensive programming in here. I say if doc type equals beer, and then I also check for the brewery ID, but there's no guarantee that all your beers have a brewery ID. So you've got to check for the attributes you're going to use, similar to a lot of other JavaScript programming. And sometimes you may actually do well to drop the type restriction. So if it just said if doc.brewery ID, it depends on what you want. Some use cases, you might want to count everything with a brewery ID, even if it's an employee, count employees and beers under the same table. Other use cases, you want to split them out. So there's one thing that I'm not really talking about in this function right now, but I'll come back to it in a second, and that's the alcohol by volume figure. I wanted to have an interesting value instead of it being empty, instead of a null. So what we're going to do later is figure out for any given brewery how strong their beer is on average. We'll come back to that. So here's that result set. This is just all the beers whose brewery ID is this random string. So it ends with 13C9. It's the same in all places, but you notice these IDs are different. So here's a beer. It's got a random ID. Here's another beer. Here's another beer. They all have the same brewery in common. If I was on the console, we could actually click through and pull up the full document. So now that we've seen how you would just query something by an attribute, I want to find the first 2 beers from that brewery, or all the beers from that brewery. It's a common thing you'll do in any database, and so now we've seen how to do that here. And we've also seen how to do some basic aggregations. I just didn't tell you that's what we were looking at. So now we're going to look at the other side of that MapReduce function. So we want to know what the average alcohol by volume on a per brewery basis is. And we can actually learn that from the same index. So this little thrill we get from answering 2 questions with the same index is fun. Yay, we answered 2 questions from the same index, but it's also dangerous. Because if you go too far down that path, that's the part where you're overthinking things and painting yourself into a corner. But here, it was easy enough. We're going to just omit null on the value, so I figured, hey, what's an interesting value I could stick there instead of null? And what could I learn from that? And it turns out that the beer documents had this alcohol by volume field that was already numeric, and so I want to average that field. That's one of the operations that Couchbase can do. So we'll look again closely at the map function and the reduce function. So we're using a reduce function here for the first time. It's a built-in reduce. We don't have any code. The code that this is equivalent to is maybe like 12 lines of JavaScript. It's not a whole lot, but now you don't have to write it, and it's a lot faster. So this text box that says _stats in it right now, you can put JavaScript in that text box, but I don't recommend it. And so there is a whole custom reduce API, and people use it, and maybe 1/4 of the time it's a really good idea, and 3/4 of the time they'd have been better off using like 3 or 4 different of the built-in reduces and doing some mashup in the application. So this stats reduce, let's take a look at what the result set looks like when you're doing that. So it's a little bit cut off here, but what we're doing as we carry forward the reduce is we're keeping a bag of numbers with us. You've probably seen this equation before in like a prob and stat class, but it's the total of all the numbers in that range, how many numbers you dealt with, the sum of the squares, and between and the min and the max. And so now you know what's the least alcoholic beer they offer, what's the most alcoholic beer they offer, and you can figure out what the average is. So we don't actually stick the average right there in the result set. We let you divide the total by the count. But in this case, for this brewery, I think the average is 5.5%. So, question? So the question is about re-reduce, and if you're familiar with the MapReduce engine from CouchDB, that's probably the thing that's closest to CouchDB in our code base. So it's the same model, but I'm really de-emphasizing the custom reduces because you just almost always shoot yourself in the foot with them. And I'm happy to talk to people. If you think you have a good use for custom reduce, you very well may. So come find me afterward and we'll talk about it. So now here's another query pattern you may want to get into. And this is actually to illustrate a couple of things. One is how to work with time, and the other one is how to do these kind of dynamic group by queries that our MapReduce engine is so powerful for. So we looked at this document last time. This is a comment, and it's got a timestamp on it. And I don't really care what that format is. Bonus points to you if your time strings sort in string order the same way they sort in time order. That's always nice. But even that is no longer that important in Couchbase. So here, let's just go in the deep end. We're querying this with group level 2, and it's giving us monthly rollups. And I'll explain what that means here in a second. And we'll also take a closer look at the function. But these monthly rollups, these are telling us when those comments were made or when those beer documents were updated. So it looks like 7,000 of them were updated, in the whatever month that is. July. Good. I knew you guys would help me out there. July 2010, some more in October and November 2010, and then another spike of 23 there in November. And so we could take this same index, this same map function, this same on-disk data structures, and query it with a different group level. And instead of getting monthly granularity, we would get daily granularity or hourly or by the minute granularity. So I'll show that here. I'll show a lot of things here. So first of all, that ugly timestamp string that we were using, how did we convert that into something that we could do this grouping magic on? And so you can do it by hand. The source code to date to array is also, maybe 20 lines of code. But it encapsulates a lot of stuff that's kind of a pain if you don't do JavaScript all day long. And it leans on the V8, the Chrome JavaScript engine that we're using here, has really good date parse capabilities. So you could throw ugly strings at it and it can probably parse it right. So first thing we do is we parse your string, or like if it's an integer timestamps, those also work. And then we break it up into an array that looks like what you see down in the corner. 1970, comma 2, comma 18, comma 17. So we take this date and we, turn it into a series of numbers for the year, the month, the day, the hour, the minute, and the second. And then we emit all those as the key in the index. So you can see what that looks like there. It's just exactly the same data that you would have in the string-based timestamp, but it's been segmented so you can do this neat magic to it. So there it is, 2012, 8/16, 22/56. I'm using dates in this example. It doesn't have to be dates. This could be anything. It doesn't have to be numbers. This could be strings. It could be USA, Texas, Austin. It could be anything like that. What matters is that it's an array. So it's separated by comments and it's got different levels of depth. So here are those group level 2 results again. It's that monthly rollup. And one thing to note is this is sorted by time. This isn't going to tell you, your top 3 most popular months. It's going to tell you all the months and how popular they were. And if you want to find your top 3 most popular months, then take all the months in your application and resort them. So this kind of goes to one of the questions from earlier about chained MapReduce. If we had chained MapReduce, it would be great at sorting those things by the value. We don't have chained MapReduce for a whole bunch of reasons, mostly about how hard it would be to get it to perform and scale on these large clusters. So people want to be able to sort by the value. We sort by the key. You'll get used to it eventually. It just means a little bit of the work moves to your application layer. Now we're going to drill in one more group level on this same index, and it's hourly. This is daily. This one is hourly here in the picture, so a little bit of a impedance mismatch. But if you really want to play around with this kind of thing, Aaron Miller, who's here today, one of our engineers, built a mashup of Reddit data. So it's like all the comments on Reddit and how much karma the person who wrote the comment has and when they wrote it. And so then you can slice and dice that by the different topic areas. So if you go to crate.im, you'll be able to see that blog post and kind of figure out how he ran those queries. And that's actually, I think, going to be a blog post series that's still ongoing. So again, group level, it's one of those things that takes a little while to grok and then has a bunch of possibilities behind it. There's another, right? So we've got group level 3, group level 4. You can imagine how that number would just get bigger, and right, you're splitting it by later elements in the array. There's also group equals true, which is the equivalent of group level equals infinity, right? All we care about is unique keys. So with group equals true, you don't even need your keys to be arrays. Like let's say in the brewery example earlier, where we were querying just by brewery ID, we'd be able to group it by that string rather than having it be an array or a number or whatever. So group equals true is like group level minus the caring about commas. So I think this is the last pattern that we are going to get into is the leaderboard pattern. So this is really common for people doing social games. You can source the data from anywhere. So imagine you have a key, it's like jchris score, right? My user ID is jchris, and it's jchris score. And every time I make a goal in the game, you anchor that key. And so then if you did a view where you take the value, right? So I kicked the goal 3 times, and now it says jchris score 3. If you make a view on that 3, right, on that value, now you can find your top scoring players really easily. So we're going to do the same thing here, but instead of game scores on a key that we're just anchoring, we're going to do it with those ratings from the beer because we were talking about that earlier. So in the previous session, we talked about how you might stick ratings on your beer. The data structure is embedded within the beer document, and it's essentially just a hash map, from user IDs to ratings. So jchris says it's a 5, Scalable says it's a 4, and Damien Katz likes, really light beers, so he didn't like it at all. He gave it a 1. And so now we can write a view to drill those bits out. So if the document has ratings, and we could also say if the document type is a beer, but here I'll take anything with ratings, it's all good. If the document's got ratings, then we're going to loop through that data structure and do that total and count, find the average rating for that beer, and then stick it in the index. The key is the average rating, and the value is the name. And the result set is going to say, oh, look, the Honey Pilsner has an average rating of 2.6. And if something else had a lower rating, it'd be below it, and other things with higher ratings would be above it. So this way, you can really, sort by anything you can compute in your runtime. So, yeah. So then, and that's a great question. We have trainings and tutorials that go all over the query options and stuff. But the question is, can you control ascending and descending? So you can control start key, end key. You can traverse the indexes in either direction. And then, of course, you can aggregate or not. You can look at the underlying raw rows or the aggregates. So what shouldn't you do? And we're getting toward the end of time here, I think, but I'll try to cover this quickly. So your reduce should reduce. It's actually really common, like maybe the first thing people do to shoot themselves in the foot if they write a custom reduce is the body of the reduce function just says return values. Right, so it's the unity reduce or something. It's not, or the identity reduce. It's not. It doesn't reduce. And when you do that, because you have to do that in Hadoop, the Hadoop model is just different. So people are used to doing that, and then they try it here, and you end up right with that B tree data structure that I showed earlier, but with everything clinging off of the root of the B tree. So there's no index, and that's not any fun. Question? Yeah. So the question is there an optimizer? There's not an optimizer. There's a warning. So if we notice at runtime that you're building up a thing that's a poor index structure, we'll start throwing warnings at you.
In test mode or development mode?
Yeah, I think in both modes. Just sort of these data structures are getting too big.
I just hate to get that in production.
Yeah, you don't want to get that in production. So reduces that don't reduce, don't do that. That's why we stick to the built-in reduces when possible. Don't try and do too many things with one view. It may feel clever, but down the road you'll be more relaxed if you just write special purpose views to, you have a feature in your application, you write a view for that feature. Again, it's always important to know that when you're dealing with disk, it's going to be a whole different performance paradigm than when you're dealing with memory. So that's why the views are so powerful for these aggregates and for doing maybe some secondary browsing capabilities, but not the real hot path that your users are going to be hitting all day long. And this is another one I didn't really talk about, but recursive queries require application code. So if you're going to be doing something based on the results of a query, and I'm getting told I'm out of time, so I'll just, I'll mention we do have a geographic index, and you can find me afterward to talk about that. And we have a full text integration, which there's a whole talk about that later in the afternoon using Elasticsearch. So come find me afterward. I think we're all out of time, but thanks for listening.